Hello, everybody. This is Jiří again. Once again, let me remind you that we are recording. So if you do not want to be seen or heard, then act accordingly. And otherwise, feel free to ask any questions during my talk. Today, we will start right where we ended 7 classes ago, when we worked with the TATOC tool. So let me share my screen. Okay. I will log in. I guess this is the correct one. Okay, so just to remind you, TATOC is a tool that allows to make a collection of text files connected with their original images, scans of the letters, and we uploaded some transcriptions along with the images last time to the system, so that we now have documents in several languages. I only understand one of them, Czech language. So mostly I will work with the Czech data, but I hope you will understand the principles. Most definitely you will understand the principles of the query language anyway. So this is the list of the text files transformed to XML. And we not only uploaded the files, but we also ran a pipeline, natural language processing pipeline, that automatically annotated the data with several pieces of information. Now we have for each word, for each token, we have lemma, part of speech tag from the universal dependencies set. We have national part of speech tag. We have morphosyntactic information like case, gender, number, and so on. And we also have dependency parsing of the sentences. Last time we used the CQL search for searching in the flat version of the data. So in the version of the data where there is a linear order of the tokens only, no structural, no syntactic annotation was used in the queries. We can just repeat one simple query. We ask for tokens where lemma is friend in Czech, and run the search. And as the individual results were the positions in the text where a token with this lemma appeared. So it was last time. Today we will go further. At the end of the 5th class, Sylvie Cinková gave you a nice introduction to universal dependencies syntactic system, and that is what we will use today in PMLTQ search. PMLTQ is it stands for Prague Markup Language Tree Query, which means that it searches in data encoded in Prague Markup Language. It's just some extension of XML. And tree query, it suggests that we will query the data, search in the data, and that the data have a form of trees. It can be, if we speak generally about the Prague Markup Language tree query, it can work with any kind of linguistically annotated trees, phrase structure trees, and any other trees, RST trees. In our case, we have dependency trees produced again automatically universal dependencies pipeline. The Prague markup language has been used for many tree banks, which I will talk about more at the end of my talk. So it goes with the system of tools, and also with several pieces of documentation. There's a tutorial, manual, some presentations. So if you like PMLTQ, you can find a lot of information on this web page. Today I will use once the PMLTQ manual just to show you where to look for some info. Okay, so if we want to search in dependency trees, we need to be able to define properties of the nodes, at least properties of a single node, and also relations between these nodes. Let's start with defining a node. We have a help to our tree bank here, show tree bank options. If we activate the help, we see that we have two node types. We will use this one. It represents a token. We could also use sentence, which represents some properties of the whole sentence. And regarding the token, we see which attributes we can define at the tokens. These text attributes refer to the whole documents, like, for example, the language of the document. And here also are some further features, morphosyntactic features, that are again on the token type of node. So we have some help here. Let's define a token node. So this is the type of the node, and in square brackets we can define properties of some attributes. We see here in the help that the form, the lexical content of the token is in attribute form. So let's say that the form again is a friend. And let's execute the query. We have two results. We see that the word is highlighted with yellow background, so you can see right away where in the sentence the query matched. The results are the individual positions in the data, in this case sentences, matching the query. Of course, we are searching in dependency trees, but here we see the textual representation. We can see it in context, clicking here. So now we see the whole document, and again the matching node is highlighted here. And we can.
I think.
Yes.
I would like to know if S tokens are considered single words, or if in this case tokens are even some terms consisting of more words, or what exactly is token?
Token is just a single word or a comma, just like in the morphological annotation.
So if I have dr he, that means that it's like that are two tokens, not one.
Two, yes, or maybe three. Yeah, 3 tokens.
Okay, which
it's
right.
Doctor, the dot, and Jiffy. So it's 3 tokens. Let's see the tree. So here we have a compact representation of the dependency tree. You can see that the word order is not kept here, left, right. And if I move it to see, oh, sorry, yeah, Dr. Tichy is a part of this tree, so it should be somewhere here. Let me move it further. Yeah, yeah. So Doctor is one node here. Tichy is another node, and the dot is not displayed. We can switch on displaying the punctuation somewhere here. Punctuation show. Okay, and now we should see also the dot. Yeah, it's here. So Dr. Tichy, it's 3 nodes. Okay.
Yes, thank you very much.
You're welcome. So this is how we search. You see that in the compact displaying of the tree, sometimes 2 nodes cover one another. So I prefer switching the horizontal placement to word order. It takes more space, but now the left-right order of the nodes corresponds to left-right order of the tokens in the sentence. So yes, we are actually searching in the tree, but we see the results first as sentences. But if we wish, we can see the context and we can see the tree. Okay, let's do some more general query. We can, of course, use any attributes available. For example, the universal part of speech. No. Okay. If we execute the query, we will get, I hope, many results. Yes, from various languages. And most of the results will be nouns. Of course, there will be some errors because the whole analysis pipeline is automatic. We need to keep it in mind the whole time that there will be errors in the data. Okay, so now we can specify a single node. We can also say, so that I can interpret the results, that text lang attribute is says, which means all the results will be in check. If I execute the query, the number of results will be lower. Yes. And the results should be in check. Now you can see that we have 3 results here, which are the same sentence, but in each sentence another noun was found. So this is one result, this is another result, and this is the 3rd result. All of them in one sentence. Okay, so now we can search for a single node. Let's proceed further. Let's express that we want to search for 2 nodes, depending one on another, one on the other. Another property of this node will be that it has a child. Okay, it's a relation between them. So a directly dependent node, you could say son or child, is another node. Again, it's of type token, and its properties will be in square brackets. Okay, I will add some spaces here and here, just to show you that this token starts here and ends here, and the embedded token starts here and here. There are no properties yet, but we can specify the properties now. So let's say we are looking for an adjective. If I execute the query, we have 160 results. And now we have two nodes in the query, and we have two tokens highlighted in the sentence with different colors. I hope you can see it as well. So the adjective, this is like different things. The adjective is highlighted with pink, I guess, and the nouns are highlighted with yellow color. So we can go through the results. In Czech, as you see, in most cases, the adjective precedes the noun. Another thing to notice is that this adjective and this noun are not adjacent in the sentence. Yeah, which is correct. What we specified in the query is that this node is a son in the dependency relations of this node. But it can be in any distance, generally, in the sentence. That's something that is very hard to capture in the CQL search. Long distance relations in the sentence without syntactic parsing, and the possibility to search in the syntax is almost impossible to catch. So in most of the results, the adjective precedes the noun. But for example, here, this is like a linguistics Indo-European. In this case, the adjective follows the noun. It may happen sometimes in Czech, even mostly if it's or especially if it's an old Czech, like in this case, but it's possible. And we may be interested only in these cases. But actually, how come that we specified the noun here, followed by the adjective here in the query, and now we have both orders of these two tokens in the results? That's because in the query we did not specify their order, actually. Again, we only specified that the adjective is in child relation to the noun. But now we want to specify the order. How to do it? That's the moment that we will look into the documentation. So let's see the PMLTQ manual. There is some tutorial, some information about user information interfaces, and there is a query language reference here. And now we will look at common syntax constructions. And there is a table with many examples. So we already know the child relation here. The opposite relation is parent. Then transitively, there is ancestor, descendant, sibling. We can say that two nodes in the query are siblings. This is a quite general relation. Same tree as. It means that these two nodes are just in the same tree without any further specification about their relation. The most general or the least specific relation we can use in PMLTQ is same document as. So with this relation, we can search for any two nodes in the whole document from different sentences, it means. Right now, we are interested in order follows and order precedes, these two relations. They specify left-right order in the tree. We could read the definition here, but without looking into the documentation, I never know which of them expresses exactly what the order I want. So I always experiment and try one of them, see the results, and see if it's the correct one. So I will specify. Now I am in the square brackets that correspond to the noun. So I will specify that the order that it is in relation order follows with the other node, with the adjective. But how can I specify it? How can I refer to the adjective no? Well, I need to give it a name. Yeah. So I go before the definition. This is the definition of the node. I go before it and say that this node is called A. Yeah. So the adjective node now has a name. Sorry, A. And I can use it here to refer to it. So this way I say that the noun is in a relation order follows with the node A, meaning with the adjective. I can put it here, or if I remove it, I can put it also here. It really doesn't matter. It can be anywhere inside the square brackets of the noun. So let's try if it's the correct relation. Yeah, we have quite many results, and we can see that the order is adjective noun. Okay, that's not what I wanted, so let's switch it to order precedes. And I will get what I want now. Yeah, only 23 results. In all of them, there is first the noun, and then there is the adjective. And now we could go through the 23 results and see if it's correct and linguistically interesting example, or if it's an error in the annotation. Okay, so this is how to specify properties of a single node, of various nodes, and how to say in which relations these nodes are. In all these queries, we saw the result. We saw the individual results. Yeah, the list of positions in the data matching the query. It's okay if there are only a few results, and in this small corpus, we will mostly get only a few results. But in larger corpora, you get to many queries, you get thousands or tens of thousands of results, and then you almost cannot go through all of them manually, and you need some to get some summary of the results, to extract some information from the individual results and summarize it somehow, get some statistics of what was found. PMLTQ has a very powerful system of so-called output filters. Let's make this query a little bit simpler, but it's the same query without the order condition again. So if I execute it, we see all the positions where there is the adjective dependent on the noun. And now I will use output filters. They go at the end of the query, start with these two signs, and then you specify what you want to extract from the results. So first, let's say that I am not interested in the whole sentences. I only want the adjective and the noun. You'll see that now I have both nodes with a name. So the noun is N and the adjective is A. So first I say that from the adjective, I want, let's say, the form, and from the noun, I want also the form. I execute the query and get the results. Now the result is a table with 2 columns, because I specified 2 things in the output filter. The first column is always the adjective, the left column is the noun. So we have the results like other things, sincere, respect, new place of work, the biggest success, and so on. So and each line in the table corresponds to one position in the data that matched the query. But instead of the whole sentence, we just have what we specified in the output filter. Of course, we can use not only forms, we can use like lemma or any other attribute. We can say, we want to know the lemma and the universal part of speech, or maybe just if I see the tree bank options, there are many attributes I can use. So let's say the feeds case here. So I want to know the lemma and the case for the position, and the same for the noun. So now I have 4 things in the output filter, so I get 4 columns, 4 columns in the result. Yeah, this is some error. Yeah, but anyway, this is again other things, and both the adjective and the noun are in accusative. The sincere, respect, both of them in genitive. Okay. The system gives us all results, or the number of all results in the data, but it shows only 100 of them. So we even cannot go through all the results here manually. Yeah. But I guess in many cases, the results, the cases of the adjective and of the noun will be equal, but sometimes not, like here. Again, it's instrumental and accusative. It may be an error, or it may be some property of the language, which is correct, but the case is somehow interesting if it's so rare. So let's specify somehow that we only want to see the cases where the results, where the cases are not equal. We can do it in several ways. We could specify the condition already in the selective part of the query, or we can use another output filter, second line in output filters, which will be applied to the output of the previous output filter. So the second filter will be applied to this table. And what we want to say, we only want those lines or those rows in the table where the value in the second column is not equal to the value in the fourth column. That's what we are interested in. For this, we have the command filter, and we simply say that the second column is not equal to the fourth column. Yeah? This way, we should filter only those lines where the cases are not equal. And yes, we have 13 results only, and we see that the cases are different, like accusative, instrumental, genitive, nominative, and so on. And now we could go through the individual results and check if they are linguistically correct or if it's an error of annotation. So you see the filters can be chained. One filter can be applied to the output of the previous filter. But still, what we did so far is to extract information from the individual results and possibly filter it. Now we want to summarize the results somehow. So I will delete this filter and I will use another construction in the output filter. So now I want to see, I want to search for any possible combination of adjective and the noun, any possible combination of their lemmas that appear in the data. And for each of them, or for each of these pairs, I want to know. First of all, I need to know the noun and the adjective and the noun. Now I'm referring with this $1 to the first thing here after the for expression, which means for the lemma of the adjective. With this $2, I'm referring to the lemma of the noun. But I also want the count, how many times this pair appeared in the data. So now I'm summarizing somehow the results. Let's execute the query. Now I don't have 160 something results, but only 152, which means that some pairs appeared more than once. Most of them, however, only once, as you see in the third column. But here, something is 3 times. It's perfect respect. So it was used 3 times in the data. 2 times, another thing, and so on. If I want to see just the large numbers or the large numbers first, I can sort the result, sort by the third column in the descending order, sort by the third column, which is the count, in the descending order, which means I will first see the most frequent pairs. And this is the result. So the most frequent pair is esteemed friend. Yeah. New Year, 4 times. Perfect respect, heartful greeting, greatly esteemed colleague 2 times. So this for expression is how to summarize the results and count their frequency. Yeah. This way we only got a long table, and most of the things were there only once. So if I want some more interesting summarization, I would have to use a more general query, not searching for particular words or maybe a complex construction. But let's say now we are searching for any node that is in Czech language. And in the output filter, I say that for any lemma found in the data, I want the lemma and its count, and again sorting by the count in the descending order. So let's execute the query now. Sorry, if I run it without filter, which I check here, if I execute the query, I see that there are over 2,000 results, which means there are over 2,000 tokens in the Czech part of the data. Now we'll execute the query with the output filter, and I get only 800 results. That's because this is how many different lemmas appear in the Czech part of the data. And you see that the most common is a comma, then there is a full stop, then there is the verb to be, preposition in, and so on. It's also a frequency table of the lemmas. I can add, just to make it a little bit more interesting, I can add also the universal part of speech that is attached to the lemma in the data. So I will add also the universal part of speech to the output and sort this time by the lemma and then by the count. What I hope to achieve here is to find which lemmas appear in the data with more than one part of speech. Again, it may be an error or it may be some homonymy in the lemmas. So let's have a look at the results. Yeah, so we see that correctly the comma is always punctuation. Yeah, let's go further. There are numbers. Here is a lemma twice. Abe is a subordinating conjunction meaning in order to. It appears 14 times as subordinating conjunction and 1 time as an adjective, which I guess is an error. Yeah, this is but. Again, it's a coordinating conjunction, and once it is noun, I guess it's an error, but we could check in the data and see and make sure. In this case, this is also a conjunction, meaning when, but maybe it may be a particle. So possibly this is correct. Okay. So these are output filters. Apart from the attributes that actually appear in the data, like lemma, universal part of speech, form, and other attributes, we can use also so-called functions that count something from the data. The list of possible functions, again, is in the documentation. I will just demonstrate a few of them. So in the selective part on the query, we are again searching for any token. Okay, in the check part. And now we want to know how many sons in the dependency tree the token has. Yeah. It can be 0, of course, if it's a leaf in the tree, or it can be 1 if the node has only 1 son. It can be 2 if it has 2 sons, but we will see how many possibilities there are. Sorry, it's written like this. If it's a function, you write the name of the node in the parentheses. Okay. So now we see that the first node that was found has 3 sons, another 5 sons, 7 sons, and so on. And we have over 2,000 results. For each token in the data, we have 1 result, 1 number. There are some zeros, of course, that's for the leaves. And there are some quite big numbers, like 7. So we want to see now which is the biggest number. It's very easy. We can order the results, or we can use also to demonstrate this possibility. We can use other functions like minimum, and it of course will be 0. So this is the minimum possible value for number of sons is 0 in our data. We can use average number of sons in the data. It's close to 0. close to 1. And now the maximum. And the maximum number is 20. Quite surprising for me. And again, if we wanted to know more, we would search for the data. We would specify here that this node has 20 sons. We would see the result in the query. We would see the tree. We would see the tree with the node with 20 sons. But we are almost out of time. So I hope this short introduction to PMLTQ was long enough to show you that it's a powerful search tool. And it has been actually used for many tree banks that you know and that exist in the linguistic world. As I said, we can use this searching tool for any data, any tree bank that is encoded in the PML format, and we have transformed many tree banks existing in the world to the PML format. And as long as they are publicly available, we provide access to them on our Lindat server, which works also in the browser, so you don't need to install anything, and you can search in this tree bank. This is a filter of languages we have. This is a filter of some other properties, like if you want universal dependencies, tree bank from version 2.2, or tree bank in Prague, dependency tree bank type of annotation, and so on. If I click on the English again, we have 52 corpora. In English, you can search. You'll see that there is British National Corpus sample, because the sample only is available free of charge. Then the Pen Tree Bank, its various parts, like the Wall Street Journal part of Pen Tree Bank. Again, if I click on it very quickly, we can run a simple query searching for the root of a tree. If I execute the query, you see the phrase structure tree corresponding to the first result. So all these tree banks are available for you. You can, of course, use the PMLTQ for your own data. You can study the documentation to find out how, or you can write an email to me if you want to know more. Okay, and so now I'm really out of time. Maybe there is time for quick questions if there is some.